Bueno, pues muy buenas tardes a todos al tercer día del panorama actual de las ciencias atmosféricas de este año 2023. Bueno, pues el día de hoy tenemos la presencia del doctor David Broday, quien va a ser presentado por el doctor Luis Ladino. Les recordamos que se está transmitiendo también por Facebook y YouTube, y quienes están en nuestras plataformas pueden enviar sus preguntas a través de las redes sociales para hacérselas llegar al ponente el día de hoy. También pueden ustedes escuchar, los que están por la plataforma Zoom, la transmisión en inglés o la traducción simultánea. Cualquiera de los dos pueden ustedes escucharlo. Y lo mismo quedarán grabadas en estas plataformas en sus distintas versiones, la versión en el idioma original y la versión traducida al español. El día de mañana les comento que no va a poder ser transmitida por redes sociales la conferencia, sino únicamente por Zoom, para que quienes estén interesados, pues tomen esto, ¿no? Pues bienvenido, doctor David Broday. Adelante, Luis.
Hola a todos, muy buenas tardes. Bueno, para mí es realmente un honor poder tener aquí el día de hoy al Dr. David Broday. So David, thank you for coming here, for accepting our kind invitation. It is really great that you are here, and thank you for coming from Israel. And I hope you fully adjusted to the 9 hours jet lag, which is something that is not very nice to handle on. Bueno, entonces voy a hacer la introducción del doctor David en español. En este caso, bueno, el doctor David es profesor y miembro del Departamento de Ingeniería Ambiental, Hídrica y Agrícola de la Facultad de Ingeniería Civil y Ambiental del Instituto Tecnológico de Israel. Es el director del Centro de Excelencia de Ciencias de la Exposición y Salud Ambiental. Sus áreas de investigación son física atmosférica y de aerosoles, contaminación del aire, modelado y evaluación de la exposición, aplicaciones del SIC para la salud ambiental, dosimetría de contaminantes inhalables e informática ambiental. Su grupo de investigación estudia métodos para medir los contaminantes en el aire a la altura de la respiración. Intentan mejorar la estimación de la exposición aguda y crónica en áreas urbanas y vehicular, así como vincular, las bases de datos georreferenciadas para mejorar la inferencia de la calidad del aire. Entonces aquí podemos darnos cuenta que el trabajo del doctor David realmente tiene mucha sinergia con algunos de los trabajos que se hacen aquí en ambos departamentos. Finalmente, a la fecha, el doctor David ha supervisado a 11 pasantes postdoctorales, 8 estudiantes de doctorado, 15 de maestría, 17 de licenciatura, y ha publicado 114 artículos revisados en revistas indexadas. Entonces, sin más, le doy la bienvenida al doctor David. David, thank you very much, and the auditorium is all yours. Thank you.
So thank you very much for hosting me here, and I'm really honored to be here. And let's start. So the topic is applying fresh perspective to common methods for studying air pollution. I must say that I present a few slides of introduction, although I know that most of you, if not all, already know everything, but it will help me to shape my speech. So air pollution starts with emissions, which we all have to remember. And emission can be either natural, of course, on the left-hand side, different sources of natural emissions, and also anthropogenic emissions. And usually anthropogenic emissions are divided to either aerial sources like agriculture, as you see here, and or domestic sources. For example, we can take traffic in an urban megapolis area and treat it as a aerial source if we want. The alternative is to use point source emissions, and this point source emission can be, again, divided into stationary emissions like stacks from industry and construction sites, oil and gas sites, or even open agriculture as solid waste burning. And then the other is mobile mobile point sources, mainly all type of traffic. It can be vehicles, and it can be rail transportation, marine transportation, and of course aviation. So this is related to emission, at least part of the emissions, or at least part of the pollutants that are found in the air. These emissions we are of course know them as primary pollutants, and these primary pollutants pass through different processes. Some of them, or many of them, I would say, are related to metrology, including dispersion and aging and removal. And through these processes, these primary pollutants are transformed into secondary pollutants. Some of them are oxidizing in there, some of them are reducing in there, some of them are transforming from gas phase to particulate phase in the air. And this happened, of course, in a nonlinear way and in a very complex way altogether. And this is part of what those environmental scientists among us are calling a long and or short range transport. So we will see that this is an issue, at least in my study area, which is the Israel, which is in the very east of the Mediterranean. And it's very unique from both climate perspective and topographical perspectives. I would just want to talk about two types of families of air pollutants. One of them is TRAP, traffic-related air pollution. Traffic-related air pollution are known to be and clearly are related to use of gasoline. So as you see here, the emission, in this case, I'm talking about CO2 emissions, but of course, we will see later that we can talk about different pollutants because traffic-related air pollution contain different pollutants. Is related, the emission of CO2, carbon dioxide, is related to the use of gasoline, and this is based on the speed of traveling, with a minima of gasoline consumption minima at about 70 kilometers per hour, and much wider minima of emission of CO2 that range between, I would say, 50 to 100 kilometers per hour, more or less. We should remember that this is only one example, and as we see here, the example of this emission, this wide minima, is for gasoline operated vehicles. If we are talking about diesel operated or heavy truck operation vehicles, we see that the emissions are much higher and someone with different minima. As I said, CO2 is only one example, and we have different examples. And here, don't look at the trends because the trend is not important in this talk, but look at the names of the pollutants that are all related to traffic-related air pollution. So we have different NOx, NO, NO2 NOx, which are also subfamily within the traffic-related air pollution, and of course particles, which are also subfamily of the this trap. And if we are moving to talk about particulate matter, we see that it's very complex because it is actually saying particulate matter does not tell us anything about the properties of the particles. In this case, I'm showing you a pie chart that actually is split more or less evenly among different factors. The factors, which I cannot see from my space, are marked here, but you see that there are different factors. And in fact, while the PM10 as a whole is, let's say in this case, is splitted almost evenly among the different factors, more or less, we see that some species which are found in the PM10 are different species have different contribution from different factors, which makes life very complicated if we want to talk about specific species or maybe specific source of the particulate matter, because particulate matter does not tell us even what is the source. This is true for PM10, particulate matter with a diameter less than 10 micron. This is true also for PM2.5, which are particulate matter with a diameter less than 2.5 micron. Here, the color code represent this type of pollutants. So for example, ammonium nitrate, ammonium sulfate, etc. They are all marked here. And And I would like to mention that this location is Rehovot, where we have a Spartan site. I know that you have Spartan site on the roof of this building too. Actually, this super site is amazing. I was there and I was really impressed. And I will discuss a little bit about this Spartan in my talk later. As you see, for example, with respect to particulate, for organics, so RM, the green one is RM, it is residual matter and was found to be related to organic material in the particulate matter. And we see that if you look at the green, it's very different. The profile is very different among different locations across the globe. In particular, for Rehovot, we see that the fraction is relatively small. Unfortunately, though, most of the time we get a quantification of particulate matter only in two physical size fractions, PM10 and PM2.5, or PM10 and PM10 minus PM2.5, which show the variability, of course, as you see here, but does not tell us anything about the speciation or the composition of the particle. And without knowing the composition of the particle, it's very hard to manage air quality because we don't know what to manage. I mean, not everything can be manageable. For example, dust storms are not manageable. So it really depends. The second thing is, as an example, is the air quality standards. Israel, as well as many other locations across the globe, are copycatting the EPA standard or the WH guidelines or the European standards. But Israel is affected by dust much more than both United States, even in California, Mediterranean climate, and or EU. So it is a big problem, and we not always can confirm or comply with the standards. So this is a big problem, and this is something that I would like to address today. The last thing that I would like to stress in my introduction is, of course, as I said, the interaction of meteorology with a observable concentration of particulate matter. And what we see here is that we can divide it, generally speaking, into two things. First of all, we can talk about the winds or the transport of air masses. And this also depends on the height. So the higher air masses from this region, the Mediterranean region, I would say something like this, go to Mexico, for example, with the Saharan dust, as I was learned today when in my talk with Luis. But there are other lower level transport in the troposphere that are taking air masses from North Africa to Europe, from North Africa to Israel, and vice versa sometimes. And there are transport of pollutants from East Europe to Israel. And in this case, most of the pollutants that are transported are anthropogenic origin and are aged particulate matter. So this is something that is related to long and short time transport. The other aspect is the stability of the atmosphere, of course, and the stability of the atmosphere is related to the dilution in the vertical direction, of course, and to the buildup of concentration. Now, I was told that I have limited time, so I skipped my first chunk of slides. Although it's written here one, I already corrected it, and I skipped my first chunk of slide. I would just want to say that in my first chunk of slide, I was dealing with radiozone data. So I was talking radiozone data from the meteorological service, the Israeli Meteorological Service, and we analyzed them in a way that they did not do before, mainly developing or looking at different methods to analyze and to find the planetary boundary layer height, different methods. Once we did it, we tried to look at what is the relationship between pollutants level at the ground measured by standard air quality monitoring station to the different types of to the height of the planetary boundary layer and to the lapse rate. And we find that the planetary boundary layer height, which is a very common parameter that is used in models by scientists that want to estimate the concentration of pollutants, is actually, at least in Israel for us, is not the best of the optimal parameter to look at the concentration or predict or estimate concentration, and the lapse rate is much better predictor. And I skipped because of lack of time, but I will touch upon it here later. So my first chunk of slides are related to application of wireless distributed sensor network, which I acronym WDSN, to identify different things, mainly factors that affect exposure to pollutant concentration. And I will show you different ways in which we use these sensors. Now, I want to start by saying what I'm not going to show you. So I'm not going to show you many years of studies that we did in order to understand how to work with this sensor. These sensors are very cheap. Because they are cheap, they decay very fast. You have to exchange them very, very fast. Very fast is within for me at least, within a year or less than 2 years. But you have to maintain them and to calibrate them in the field every week or every 2 weeks or every less than a month. So the calibration decays much faster than the sensor itself. And you have to do it in the field, because if you calibrate them in the lab, you don't expose them to the soup of pollutants that are found in the field, and they are very sensitive to the soup of pollutants. So you need to calibrate, at least for us, we found that we need to calibrate them in the field. I'm mainly talking about sensors that are measuring gaseous pollutants, less about sensors that are measuring particulate pollutants, optical counter like this one, which was the first one that I used, and I will touch upon it here. So we deployed different similar sensors like this. This is the optical counter in this neighborhood. As you see the scale, this is 1 kilometer. So it is less than, I don't know, 2 by 2 kilometer in the neighborhood, a residential neighborhood in Haifa. Topography is rather flat, apart from these wadis, or this, low-level topography. And we see here in red the different location when we deployed the sensors. All in all, over the time, we did have more than 10, about 11, but some of them died very fast, and we were able later to work with only 7 or 8 or something like this. Nonetheless, I would like to say that in this neighborhood, there is one official air quality monitoring station, which is, of course, not existing in any neighborhood. It's only limited number of neighborhoods. So we were able to compare whatever we do with this standard measurement and be able to say whether the measurements are okay or not. And because we already calibrated them in this place for a long time, and we recalibrated them and rechecked, etc., 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 we were able to say what is the natural variability of the sensor and what is the beyond the natural variability of the sensor, which is the true variability of the environment. So by deploying them in such a way that they cover an area, we can actually learn about the variability within the environment. Now, I want to stress this is variability, natural variability within 2 by 2 kilometer grid, true urban grid. The sources of variability. So everything that you see in this big and busy table is statistically significant, apart from the things that are marked by yellow. So everything that is not marked by yellow is statistically significant. And we did the statistical significant to those that are interested, either by using Kruskal-Wallis, which is a non-parametric one-way ANOVA of ranks, because it's not distributed normally. And we also use the mean coefficient of variation. And these sensors give us 2 ways to looking at the data. Either we can look at the PNC, which is the particle number concentration, so actually measure number of particles, so it's number concentration, or the sensor itself, through its algorithm, can translate it into a particulate mass with particles less than 2.5 micron diameter. And this is compared to the standard measurement of particulate matter, which is given only in mass terms, so PM2.5. And what actually affected the variability across this small piece of the neighborhood, or small neighborhood? A lot of meteorological parameters. So we see here synoptic patterns, so different synoptic patterns. Some of them, at least for the PNC, were not significant, but the winter storms were significant, and even the red street trough and the winter height were significant if we are looking at the mass concentration of the reference site and of the optical counter. Wind direction, wind speed, of course. And so these are the simple parameters, simple meteorological parameters that are measured in a standard meteorological station. We looked at the weekends and weekdays, which are representative of anthropogenic activity, of course. So we see that there are variability across the neighborhood, different variability in the weekdays and in the weekends, and they are all significant. And we looked at that, split the data into daytime and nighttime, a very simple split of 6 a.m. to 6 p.m. So it's a crude split. And of course, daytime and nighttime is not only anthropogenic activity, because the sun is also affecting the nighttime and the daytime, but still we see a variability, the difference in variability in the daytime and the nighttime. And these are the drivers of variability across the neighborhood. Now, it is very clear that, or very expected, that we will see variability in neighborhoods extent, but oftentimes we do not look at it in this way. We plug maybe 3, 5, 10 air quality monitoring stations in this big city. I don't know actually how many there are in Mexico City itself, but let's say a couple of tens. But clearly there are not one in any, and in all neighborhoods. And still this neighborhood do suffer from variability. So this means that some locations in the neighborhood are more pollutant than other locations. And now it really depends on the socioeconomic status of the people, whether these people that are more vulnerable live in this high level or high polluted area or low. This is very important with respect to environmental health issues. So neighborhood scale spatial heterogeneity of particulate concentration is related to wind field at multiple scales, because we are talking about a synoptic scale and local scale, and to human activity, of course, through the variability of emissions, because emissions are also variable. They are not homogeneous emission even across this residential neighborhood. So we wanted to dive into this a little bit further. And what we did here is we changed the location of the deployment, and we see this black box, black rectangles are the location of the deployment now, mainly along one main road, but not only. And what we see by simple box plot is that the mean, the median, and the interquartile range is very similar both across these 5 locations, both in the weekdays and in the weekends, more or less. Of course, there's difference between weekends and weekdays because there are very few weekends in any given period, many more weekdays than weekends. So the statistics of the weekends is obviously based on 1/5 of the measurement or something like this. But more important is that in both weekends and weekdays, we see that the main variability is coming from it's maybe not outliers, but the high end, the high percentile of the distribution. This is actually what driving the big variability. And well, maybe it's important to see where this high percentile are coming from. And to do this, we actually run through a wavelet analysis. You well know that wavelet analysis is a method in which you can actually split the data into different. You split the data based on the window size, which is in this case is the time scale. So the window size represents the time scale, and then you see the spectral structure of the data. And this is one example. So you see here 3 months from June to, sorry, from 1st of April to June, or from the end of March to June. This is the time series, the true time series measured in one of these sites, actually in these sites probably, and the wavelet spectral analysis mapped. So what you see here, the color code, is the wavelet coefficients. And the time scale is in the y-axis, and the true time, the dates, so the true time is in the x-axis. And we see very large, for example, very large intrusion, which is the high wavelet coefficient in red in this time. This is a desert dust storm that hit this area. And the intrusion is actually seen from the synoptic scale. So 144 hours is about 5 days, or actually 6 days, I think. So it's a synoptic scale. And we see it from a synoptic scale in penetrating to the half day or even less scale. We see that synoptic patterns actually can, not all of them start at 6 days. Some of them start at 5 days and then decay, etc. The interesting is to see is that we see the variability across the dates in this large time scale, say from the synoptic scale to the daily scale, I would say. And at least for with my data, we didn't have good data at a high resolution, temporal high resolution, so we couldn't reproduce the turbulence scale, because turbulence scale is of course less than 1 hour, but we couldn't reproduce the turbulence scale here, and it seems to be very homogeneous or very flat. We can do it also with another tool, which is called polar plots of the mean particulate number concentration. And this is all the data from the previous slide, and we see huge variability. The polar plots is actually each circle or each point is the concentration that is at the distance of the radial distance from a central of the city or central of what we want. And in this direction, so the wind is blowing in this direction. So this is what we call polar plots, and we see heterogeneity that is related to the wind direction, because different winds bring into the city different pollutants. This is more visible or in the long scales, longer than say one day, and we have seen it previously in the synoptic scale. It is still visible in the sub-daily scale, but it's not visible in the 1 to 4 hour scale, which is more, I don't know, approaching, let's say, the whatever we call turbulence, although turbulence is much finer scale, of course. The last thing that we did in this, and find it very interesting, is to do it's called coloregram or correlation of wavelet coefficients. So we took the wavelet coefficient of we took this wavelet coefficient, this one. We took the wavelet coefficient and from one station, and we compare them or correlate them with the wavelet coefficient, with the wavelet coefficient of the wind data that we measured very nearby. And we got these plots. The difference in color is because we did it separately for 2 periods of time. So let's focus only on the black, which is more understandable for me, at least. So we see here positive correlations here. This is 0. So we see positive correlation for continuous wavelet transform scales, which are 72 hours, 60 hours, etc. So more than 1 day. So synoptic scale. And these are positive correlation, and I call them long-range transport, because at that scale, the synoptic winds or the patterns are actually bringing or taking pollution from the measurement site. So this is expected to be positive. Nonetheless, looking at the same data at a different scale, for example, at the daily scale, we see the dispersion, the daily dispersion in the half-day scale, the 12 hours, we see the dispersion, which is, of course, a lower scale meteorological phenomena. And we see that for the lower continuous wavelet scales, we don't see much. There is some interesting features here, but generally they are very close to zero, so we don't see much. They are more related, in my eyes, to wakes, which is a certain type of turbulence, patterns of wind that is actually cannot cross objects, and they have to go across buildings, trees, border, bridges, etc. So this is a, let's call it horizontal turbulence rather than vertical. So I think that this is related to this feature. And in general, my operational, I call them, conclusion is that PM pattern in urban areas are highly dynamic due to varied emission rates and varied emission locations. Aging processes and formation of secondary particles. Some temporal patterns can and are captured by wireless distributed sensor network, which is good. We want to have something that can be measured by this sensor with this sensor, and we prove that something can be measured, especially maybe long-range transport and maybe background. The variability across the neighborhood materialized mainly in the upper percentile of the PNC distribution, as I've shown you. And the question was that we asked ourselves was, okay, what else can we do with these cheap and not so good sensors? So can we combine their data, the WDSN, the wireless distributed sensor data, with other data sources, and how? And can we use them to learn about pollutant sources? So the first question was answered in this work. What we did is we actually fused land use regression modeling. Land use regression modeling is LUR, as you all know, which is stationary, because in normal land use regression modeling, you don't have temporal data. You have only stationary data. Density of people, roads, density of vegetated area, trees, etc., but not so much temporal data. So the land use regression was a very stationary model, and we combined it with data from wireless distributed sensor network measurement. In this case, we'll see that it is not particulate matter, but NO2, to produce fused. You see here the stationary, the land use regression, which is stationary, is actually similar throughout the day. This is a typical day or typical 1 day. The red is our sensors data, and we see variability. This is after calibration, of course, but we were not sure that the variability is fully correct. We fuse them together. So this is the black, this is the fused, the blue and the green and the red fused. I'll show you in a minute how we did it. And then we were lucky to compare it to true data, AQM data, Air Quality Monitoring Station standard official data, which were also apparent in this location, this neighborhood study area, which is the yellow. And we see that we manage sometimes to be better than the black is sometimes better than the red, sometimes worse than the red if you compare it to the yellow. Overall, if you just look, this is to be very, very strict. If you just look at the fused data in red and the blue data, which is the true data and the standard data, they look visually very nice. They follow each other very nice if you don't dive into this type of looking very in a detail whether you actually did correct or not, or whether it was full, by chance. Basically, the algorithm, just to those that are interested, is the following. We take the land use regression model, which is stationary data, and as you see, is rather flat, not so much colors. We combine it with the spatial interpolation of our sensors. The interpolation was done very, very simple. It's called inverse distance weighting, IDW, inverse distance weighting, which is the most simplest geospatial interpolation method. And of course, you should not believe these contours, because they are based on this type of interpolation. Other interpolation types will give you different contours, but they clearly show different things than this model. We subtract one from the other and got this residual, what we call. And then for each green point, we compared the residual and said, okay, the residual is larger than zero or smaller, sorry, larger than zero and smaller than zero, whether we are, whether the land use regression is overestimating or underestimating. And in this case, for each cell, we could give a correction factor. The correction factor in these two cases are always between 0 and 1, and this is fuzzy logic. So we follow the fuzzy logic algorithm, and we combine this together. So the land use regression minus this factor, the Q, times the residual, and we got this map, which is hourly example of fused data. Now, it looks much more rich with respect to depth and colors. It doesn't mean that it is true, but it looks much nicer than both this and this. And then we were lucky to have 4 RQM stations in this study area in triangles, 1, 2, 3, 4. So at least in 4 points, we were able to compare our fused data, which it never saw the true data, never saw. It is based on one model and on another model based on measurements from the sensor that we bought, not from the official sensor. So they never saw the AQM data, but in 4 places we could compare them. And what we see is that the land use model, so the left column is mean bias, the middle column is root mean square error, again in ppbb, and this is the correlation coefficient. And we see that the land use regression model was very, very biased. You see the 0 is here, and compared in these 4 places where we can compare it to, you see that most of the data were biased to the negative. So they were actually, what was it? Negative would be underestimation, overestimation, whatever. The WSN was more normally distributed, I would say, and the fused data was normally distributed or more normally distributed also. So actually the fused data capture the feature that was provided by the WDSN data and kept to be more normal distributed. Similarly go with the RMSE. The land use regression model was biased, or the RMSE was positive. So we see this is the 0 and everything was above 0, of course, positive. The sensor also was, RMSE was positive, but a little bit less slanted to the left or more close to 0. And the fused data combining this and this captured this feature and was actually less biased than the land use regression modeling. And with respect to the correlation, it turned out that the land use regression had overall the distribution was better than with respect to correlation value closer to 1, better than the WDSN, and the fused data. Combine them together. Of course, it was linearly, but non-linearly, because talking about the space, each cell got a different correction. So talking about each cell here, each cell here got a different correction factor. So if you look at the system itself, it's non-linear because every place is correct differently. So although the correction feature is linear, it's fuzzy logic, it's trapezoidal or something like this, the overall total effect is non-linear correction, and we see that at least here we see that it captured it nicely. So this was the second application of WDSN, and this is the third application. We said, can we use them to learn about sources? So we got a question from this city. This is a small city in Israel that is actually very close to Quarry, Stone Quarry. These are less than 2 kilometers, as you see here. This is 1 kilometer, so this is less than 2 kilometers. And they were very worried that their children are affected by the quarry and that might be some health effects, asthma, etc. They ask us to tell them the truth, whether it's affected or not. We tell them that I don't know the truth, but I can estimate at least to my best whether it is affecting or not. And we did it by deploying 3 units here, again, optical mass counters of particles, one here and one not shown here very far away to serve as a background. And first of all, we looked at the correlation map, and we see that these three units were correlated among themselves very nicely, both for the fine fraction, the F stands for phi fraction, and these three units also correlated among themselves with respect to the coarse fraction. So we learned that, at least from a simplified way of looking at it, we can choose any of them and it will be as good as any other. So this is what I will show you later. Then we looked at the three in the city, the three sites in the city. The site EIN is this site, and RIB is here. And we looked at the data for a while. I think it was for a year, if I'm not mistaken, splitting it to fine fraction and to coarse fraction and to working days and Saturdays. The query work only in working days. And well, it seems to be that the query is affecting. No, I mean, it's always, the blue is always higher than the black or whatever it is here. So the first guess would be that it is affecting, but it's clearly not true because, or clearly not, I cannot say it based on this analysis, because we see that it's always higher, even in very far location from the query. So if something is causing the working day fraction of fine and coarse, by the way, to be higher than the weekends, it may not be the query. We have to double check it. So we looked at the wind field, of course, again, for a full year. So the daytime is coming from the northwest, the nighttime is coming from the south-southeast. And with this, we built this plot, which is actually the concentration for a given 10 degree sector. So you see here that every 10 degree, we have a value. So we average over the full year over 10 degrees. And I'm showing you only two sites. This is the RAB is within the city, and the EIN is the other side of the query. And it is interesting that both for fine particle number concentration and for coarse particle number concentration, the blue line is always higher apart from here. The blue line is always higher than the red line. So the measurement in this site are always higher. In fact, they are higher for fine fraction and for coarse fraction, but in query, we expect to have more coarse fraction than fine fraction. And it's also interesting that the blue is higher for the coarse and for the fine, I would say, during the time that the red, this city, is downwind of the query, and also when the city, the red, is upwind of the query. So this actually means that, for us, this actually means that the query does not affect the city, because the situation is not related to the query, it's related to something else, which we are not we were not studying, or we're not worrying about, or we were worrying about, but we couldn't answer by our data. So this is another aspect, or another example, what can be done with this small, stupid, sorry about the word, but this small, cheap, and not so good sensors, I would say. So my conclusion is that WDSN data have great potential to complement other databases by providing complementary information. However, deploying a large network is not as cheap as thought, not because the sensors are not cheap, because the labor is not cheap, because deploying big network requires a lot of people to maintain them. And I really mean that this is weekly maintenance and weekly, maybe every third week calibration in the site. So labor is a major cost. Where labor is expensive, labor is a major cost, of course. Compared to the cost of this sensor, always labor is a major cost. Sensor lasts for limited time before they need to replace. and the sensor deployment requires collaboration with the municipality or the electric company or the environmental agency that owns everything in the street. It can be the street lamp post. We posted them on the street lamps post, or traffic lights, or traffic signs, or street trees, or whatever. I mean, you need to get the permission, and it's a lot of bureaucracy, even everywhere. So the next would be to look for us. I mean, basically the next thought was to look at an alternative option that can provide extended spatial cover at reasonable temporal cover, and which is much cheaper. So we went to remotely satellite remote sensed data for improved exposure estimation. So truly, it is not everything in my career is not so nice. Developed in a nice line. It's always very chaotic, but conceptually, it's nice to present it like this, so that you think that I'm really know in advance where I'm going. So this actually shows that what we do actually with satellite products. So if we take aerosol products from satellites, normally it is the aerosol optical depths. AOD is the aerosol optical depths. And we try to build in a way, a model, empirical model, that connect the aerosol optical depths, which is a satellite product, with particulate matter, which is measured on the ground. We all know that there is a chances that we will not succeed, because the aerosol optical depth is a columnar measurement of the whole atmospheric column, and the particulate matter on the ground is, in good cases, in good chances, is that it's measuring some local measurement. So, but everyone do it. So everyone does it. So I did it too. And what we see here is a type of a mixed effect model, which actually the important thing about it, it is very much used, let's say 5-7 years ago, even 10 years ago. And what it does is actually, it's supposed to be, or similarly, or seems to be a linear model. And indeed it's linear model, but it's tricky linear model, because it is considering the measurement and taking them at a different scale. So if you look only at the average, you can use, for example, intercept and the slope, time the AOD, and this will give you some measure of the average, and then you can take the residual of the measurement from the average and try to look at intercept and slope of different averages, time averages, for example, monthly average or daily average, and add other parameters that might be related to, that have temporal variation. For example, all the measurement, all the type of parameter that you see here, all of them are methodological. This is the columnar water vapor. This is, of course, aerosol product or a satellite product. Wind speed, relative humidity, planetary boundary layer height, surface pressure, wind direction, NDVI, the difference in vegetation index. Again, aerosol product, temperature and elevation. So the bottom line, this is done with the colleagues in India. So the bottom line show you that actually this model works quite nice, because if you do a R-square compared to the true measurement, we get above 75%, which is considered to be quite nice for environmental data. It's not lab data, it's environmental data. So it's quite nice. And this is actually cross-validated, either on the left column, it's cross-validation by sample base, so we choose 20% of the sample without looking at the structure. And on the right-hand side is site-based cross-validation. So we took out specific sites, 10 to 20% of the data in specific sites, and so this has some spatial structure. And in both cases, we see that the results are very similar, and we see that when we use machine learning models, which is the new buzzword, it's regression type machine learning model. In this case, it was random forest model. We got better results. So it's a 0.87 or something like this. So we know that we can do it, and we did it multiple times in different data. But this is, again, does not tell us much, because we showed previously that PM is not enough. PM does not tell us the whole story. So let's try to do it fast. So we try to look and see what affect the PM and what affect the measurement, the satellite measurement. I will skip because I don't have much time. I think that I would. Okay, so let me say something like this. So we used MODIS data. MODIS is the specific sensor that is mounted on 2 satellites. We use only 1 satellite, Aqua, for certain reason that I will explain in a moment. And we use one algorithm, retrieval algorithm, the newest one, which is called MAYAC. And this MAYAC algorithm actually do classify the aerosol into 3 types, but it reported, but most of the people that work with satellite data do not manage or do not care about it, do not use it, I would say. At least we didn't find any publication that used it previously. So the 3 categories that the MAYAC report is 2 global types, dust and smoke. And I'm talking about global type. This means that the physical-chemical properties or the refraction index is global wise. I mean, there is something about dust, there is something that's related to smoke, and these are global types, and 1 local type. Local type is actually based on local, and because it's local, it has NASA use 8 different sites. For example, Mexico is the 3rd, not the site, the algorithm, and Mexico is in the 3rd algorithm, in Israel in the 2nd algorithm. But the 2nd algorithm we see is also United States and South Africa and Australia, etc. The interesting to look at is 2 episodes that will give you some idea about what is happening here. So this side, the upper row is California. It's a forest fire in California in 18th of August 2015. The lower line is a dust storm over North Africa on 23rd of June 2003. And this is RGB picture. So this is actually true pictures. And we see dust storm, especially we see it over the Mediterranean because the contrast is much better than over the land. And we see something here, which those that have sharp eyes will say, okay, here we see some smoke, but we don't really know much maybe about what we see. What the AOD reports, the retrieval algorithm reports, is that this is the AOD scale, and we see high AOD here, actually where the fire is, and we see higher AOD here, actually where another fire is. And if we were not, you don't have sharp eyes, maybe we missed this feature. And it reports very high dust, but this algorithm, retrieval algorithm, is working only over land. So we don't see the retrieval over sea, but we see over land high AOD, which is harder to see here because of the reflection of the ground and the color of the ground, but there is high AOD. Now, the interesting thing is that if we look at the characteristic of what is the aerosol type, we see that in California, the aerosol type was smoke, red is smoke. And in North Africa, the aerosol type, the blue here, is dust. Don't look at this. This is, of course, artifact of the retrieval, but where the retrieval was okay, the blue describe it as dust. So that means that actually satellite retrieval can actually tell us something that was not used before. And this is the type of the aerosol type that is some sort of chemical properties or thermophysical properties, or maybe toxicological properties, or maybe source, or maybe health effects related issues. So there's something in this. So we were trying to look at this, and what we see here is comparison of 2 aerosols, the product of 2 aerosol, of 2 sensors from 2 different satellites. This is Calliope, which is a sensor and a satellite that is called Calypso. And this is MAYAC AOD, or MAYAC based, that is operating on MODIS sensor that is mounted on Aqua. The nice thing about Calypso and Aqua. And the next satellite that I will show you, that all of them are running in the same polar orbit, which is called the A train, the afternoon train, and they are passing each other within few minutes. So from a satellite perspective, they're actually co-measuring it simultaneously, although they are in different satellites. So basically, we have different sensors that measure almost simultaneously the same scene. Calliope is the only sensor that is active sensor, and it gives much more rich information. So they can split the measurement, the types of the aerosol into 7 types. Unfortunately, in the whole 15 years or 20 years of data that we looked at, we only identified 5 classes out of the 7 possible, but these are the 5 classes. And we see that with respect, so this is Calliope, this is Biac, and the y-axis is the angstrom exponent. The angstrom exponent is a spectral AOD feature, which actually tell us about the size of the dominant size in the aerosol. So we have coarse aerosol where the angstrom exponent is less than 0.7. We have fine aerosols or particles when the angstrom exponent is larger than 1.3. And we see that, first of all, the dust, blue is dust. Dust in Mayak, DD is the desert dust in in Calliope. And we see that the dust is indeed nicely identified from all the other types. Both because it is raw coarse, the AE is less than 0.7, so it's coarse particle, and we expect dust to be coarse particle. And it is distinguished from the other types. And if you look at Calliope, for example, the other types, the mean and the interquartile distribution is not so much different, and it might be very, very complicated to identify this type only by size. Of course, they are not identified by size only. The problem with Calliope is that the footprint on the ground is very limited because it's only 5 kilometers. You don't get full cover. So we didn't want to work with Calliope, and we went to work with another satellite, another sensor. It's called OMI, Ozone Monitoring Instrument, which is mounted on satellites named Aurora, which is also part of the A train, and it has full cover. And we combine the measurement of OMI on Aurora with the measurement of MODIS, but in this case, we use a different retrieval algorithm. It's called the Deep Blue, and the Deep Blue gives us angstrom exponent. And if you combine 2 different independent measurement of the size angstrom exponent and the measurement of the what is called aerosol index made by OMI, which is related to the optical properties, absorbing or scattering, we could divide it or build 9 classes of aerosols, absorbing coarse, absorbing fine, absorbing mixed, scattering, and neutral, which is neither absorbing nor reflecting, nor scattering, and compare it to Mayak, and I will go very, very fast. And we see that this actually is much richer. The table shows you much richer, although Mayak gives us some problem. Mayak is known to be problematic. For example, when Mayak report dust, it's oftentimes absorbing coarse, which is good as we expect, but dust can be also neutral fine, which is less expected. With respect to the background, it's working much better. The background in California, most of the background is either absorbing fine or neutral fine. We expect absorbing fine to be anthropogenic, but also in Germany the same. Also in India, South Asia is India, we see that background is absorbing fine. So it seems to be that maybe by this categorization we can get much better results. I hope that I have a few more minutes. So we went with former PhD students to do this modeling. We developed, in this case, 13 models where we split the data along these lines. First of all, the first model used the whole data, all the data. And these are the input data. You see the AOD, the columnar water vapor, planetary boundary light layer height from models, from a modeling, it's a model input result. temperature at 2 meter height, etc., etc., etc. Overall, we had a little bit less than 48.9 readings. So it is a nice amount of nice big N. So it was nice to work with it. Then we said, okay, we can do the modeling based on this data, but we can also split the model supervised by just looking at the different reporting aerosol type that they already provide us: background, dust, and smoke. So these were 3 models. And as you see, the data is splitted such that the background get much more than all the others over Israel. But the sum of all these 3 is exactly the same. So we can combine the weighted results from here with the baseline. Then we said, okay, let's add the deep blue based aerosol angstrom exponent. Of course, by adding this, we were limited by the number of data, because now we have to use data from different instruments on different aerosols. So it happened that we split the data by almost 4. And again, once we did it, we can look at the whole data, and we can look at the coarse fraction, the fine fraction, and the mix size. Again, these 3 are combined. All these 3 combined are the basics, so we can compare them. It's important to note it. Then we added the OMI UV ultraviolet aerosol index. It is further downgraded from 10,000 again by 5th to about 2,000. Unfortunately, we were not able to develop model for all types of optical particles, only for absorbing. Only for the absorbing category and for the mix behavior, and not for the scattering, because we didn't have. So here the sum of these 2 is not equal to this. And then we could go further and try to look at this, but we were not able to do all the 9. We were able to do basically only 2, as you see here in number 12 and number 13. And the number were very small. And for machine learning data, for a machine learning model, the number of data is critical to do all the parameterization, and this is actually a limitation. Very fast. We performed 2 types of, on this 30 model, we did it both in random forest and in XGBoost, 2 types of machine learning model, different in a little different in philosophy. And what we see here is that this is the basic model, adjusted R square. If we look at then we had 3 models that look at different aerosol type, and we combined them together because the data was the same. So the training set and the testing set, everything is cross-validated. So the training set of number 1 is exactly equivalent to the training set in number, to the training set of the number of the combined 2, 3, and 4. And we see that we improved the R square. We went to including more information by adding the angstrom exponent instead of the split into aerosol type of MODIS, which was proved to be problematic. Sorry. Yeah. It's true also for the normalized root mean square error. We improve it because it is smaller. We went to the model 5, which is the angstrom exponent. We further improved the results in R square, and we further improved the results when we built different models to the 2,000 to the 10,000 data here. Yeah, we built 3 different models for the absorbing, scattering, and neutral, etc. Sorry, for the coarse, fine, and mixed, and further improved the model. So the model further improved, and of course the normalized RMSE also improved, compared even to the baseline. And basically this shows that if we split the data, it can be either based on product that we observe, or by product, or that NASA report, or by product that we built by fusing different data types, different data product, we could improve the overall results, the overall prediction. This is true also for the different line of model, the XGBoost, but I won't go over it. But you see that we improve from 0.74 to 0.8 to 0.85, etc., etc. So there is some idea behind building a spectrum of models that deal with different types of aerosols, different composition, basically, rather than with building one model that will treat all. So one model does not fit all. This is basically what I want to say. This is this is an example of how we can then use the model and perform it and run it for the state of Israel for the whole year. So this is an annual average. We see that the model provides visually different types of maps, but rather similar, I would say. And we can choose one of them, for example, the XGBoost, and we can plot the model number 5, which is all the aerosol type plus the angstrom exponent. And then look only on submodels of number 5. Model 6, the submodel of number 5. Number 7 is submodel of number 5. This is for the fine, this is for the coarse. And naturally, we see that the coarse data, the coarse aerosol is found in the south. In Israel, south is desert. So it's found in the desert. The fine aerosol is found in the north of Israel, I would say, where people reside. So most of the population actually resides across the shoreline, or along the shoreline, I would say, and all the industry, everything, all the life is actually happening in the north. Very few people reside in the south. So it seems to be interesting, and we can also show it when we add the angstrom exponent and the aerosol index. So for the absorbing category. So the aerosol index. So this is the number 10 with the whole model. And then we're looking at absorbing coarse versus absorbing fine. And we see that the absorbing coarse is in the south, which is, of course, related to dust, probably. And the absorbing fine, which is related maybe to anthropogenic, or as the best I can say is some sort of anthropogenic activity, not necessarily traffic, is at the north. So it seems to be working quite nice. I will jump this because I don't have time, but we improved over previous models, and we see that basically this idea can be actually working quite nice. And I will just I would just like to say that this is again, this is not this is one. Using satellite data is one way to approach the problem of wanting to have a full cover, full spatial cover at reasonable timeline or time resolution, which is 1 day in this case, because satellite pass only once per bay in a daytime hours. And the other aspects, which unfortunately I would not be able to cover now, is that we can still use our AQM data, which is we have on the ground, and do source apportionment by AQM data. The main difference that I wanted to present, but I will skip it, is that there are many people that are doing a source apportionment based on AQM data using the most common is the PMF, the positive matrix factorization method, as you may know. But this is done only when you have chemical composition, because PMF is built to work with chemical composition. And if most of the countries, most of the locations do not have very rich chemical composition data of emissions, or especially of particulate matter, the PMF is not necessarily the best way, but a very similar family member is a non-negative factorization method, and you can use this, and the information you now use is not the composition, but the covariate composition, covariate information. So we use covariate that are actually based on either long-range transport sectors. So you see we have here 5 or something long-range transport sectors, and sometimes we used information with respect, information with respect to measurement of Spartan, which I said that I will touch, but I don't have time. But Spartan is here in Rehovot. Spartan site that we have. And one aspect is, of course, how many factor to use. Normally, people choose whatever they want. We used, maybe not normally, but I read a couple of papers where people specify the factor without providing real evidence why they choose this number of factor. We used the ICAC information criteria, which actually showed us that in the non-summer synoptic patterns, we should use 4 factor, and in the summer, the dashed is summer, and in the summer synoptic pattern, we should use 3 factors. So actually follow this recommendation or this idea, and in the non-summer, we see 4 colors, in the non-summer, we see 4 colors when there are 4 colors. It really depends on the station across the Israel, and in the summer, only 3. And the main point is to decipher what are the factors, and deciphering what are the factors is actually the big chunk of information that is missing. And I show you only the following. If we look at the timeline, a typical day for a typical synoptic pattern from our data, from the data that we use, we see that, for example, factor 1 has a peak at around morning peak at around 8, and then another peak at around evening. This suggests, but not prove, that it might be related to urban anthropogenic activity, but this needs to be rather rechecked. We look at the factor 2, we see that it's rather flat, but distinct with respect to the different synoptic patterns. And also there is no weekend effect. So look, in the factor 1, we had a weekend effect. Don't see any weekend effect. So for us, our prediction or assumption or guess was that it is related to background and long-range transport. In this case, non-summer, because you see that we have only solid lines. So this is the non-summer factor 2. Again, based on this idea of temporal patterns in daily, weekly patterns, this is the land sea breeze circulation, we think. And I will discuss it. I won't have time to discuss it, I'll show you in a minute. And number 4 is the local or proximate sources to the east, because it's evident only in the red mainly. And red is the east sector or synoptic pattern from the east, so it probably reflects something in the east. This is the non-summer. For the summer, which is the dashed lines, we see different patterns, and we see that actually F2 sub S, so factor 2 summer, factor 3 summer, seems to be very similar, although we couldn't split them in the factorization. When we tried to split them, we got very bad results. The only good results were when we actually forced the 3 factors, factor 1, which is general, and factor 2S, factor 3S. This is the only time when we got the results, although the results are very similar among them. To finalize, we had to, and we related to long-range transport. We wanted to prove it, so we look at the Spartan data. Spartan give us speciation, and for example, with factor 1, we see a lot of equivalent black carbon, and also in the non-summer organic matter. So it seems to be that our guess, based on the temporal pattern, is supported to some extent by the Spartan, and same goes to the other. If we look at the feature importance, the permutation importance, or feature importance, which is a feature of machine learning models that actually give you what are among the parameters give you more contribution to the final results. We see that for factor 1, for example, the feature importance says that NOx, which is a covariate, is mostly related to the factor 1, which again give us some evidence or some support, I would say, that factor 1 is anthropogenic and maybe related to traffic. And we see here another type of valuation type that we did with factor 2S summer versus the ammonium sulfite and the sulfate from the Spartan measurement. And we see that we get some nice correlation, which actually suggests that factor 2S is related to, not to ammonium sulfate, but to things that ammonium sulfate represent. Either they be long-range transport from Europe or local emission from agriculture or whatever, but related to ammonium. I'm getting to the why I'm bothering with this. This is the main issue, because I'm interested in environmental health, and I'm just showing you that we did a lot of work. This is a collaborative work. I'm not an epidemiologist. I never touch epidemiology because I really appreciate epidemiologists that do this work much better than me. But by looking at the pollutant and being able to say this is traffic, this is dust, this is industrial, etc., we can actually give much better information, even with respect to environmental health. So we see, for example, asthma and related to nitrogen oxide. We see air pollution, which is actually here was nitrogen oxides with respect to autism. We see exposure to industrial air pollution, and we actually marked industrial air pollution by markers of industry in relation to asthma and atopic diseases, traffic-related air pollution and pregnancy loss, cancer mortality related to traffic air pollution. It's traffic air pollution, etc. So I'm sorry that it took too much time, and I thank you for being here and for listening to me, and thank you.
Hola, bueno, hay una pregunta. Bueno, thank you very much, David, for your nice presentation. And so now it's time for questions from the auditorium first. ¿Hay alguna pregunta para el Dr. David? So I have one for internet. So let me check here. Where is it? And this is related to the first part of your presentation. And so it's coming from Joshua, and he said, what is the wavelength range of the wireless instruments?
The wavelength length of what?
The wavelength range of the wireless instruments.
So I assume the question is related to the particle measurements, because the particle are optical. And I must say that I don't read exactly the wavelengths, but they are in the V's near range, because this is the best wavelength to measure aerosols of about 1 micron or something. The instrument that I use measure from 0.3 micron to 20 micron, I would say. At least this is the manufacturer specifications. For this particle size range, the wavelength that is fitting is somewhere where the me ratio, or actually the size between the particle size and the wavelengths would be closer to 1. So it is somewhere between V's and near range. That's I would say. But I don't really remember. It's very limited because it's just a moment, I'm missing the word. It's it's limited because it's not laser based, but it's very narrow wavelength. So it's okay. I don't remember. The simple answer, I don't remember, but it is in the V's near range.
Okay, thank you. ¿Alguna otra pregunta? Allá atrás hay una.
Yeah, thank you very much for your. I have a general comment and a question. It seems that a lot of your data has a lot of uncertainties. Somehow that compels you to use some other methods to consider uncertainties. Among these is the forestry's analysis, and probably you mentioned like going like that fuzzy logic and analysis with basically it should help in dealing with these uncertainties. Can you make a comment about these not traditional, let's say, ways of doing statistics?
You're perfectly right. I'm working with real data. Real data had a lot of uncertainty and a lot of variation. My belief is that it's better to work with real data than to work with artificially produced data, although it teaches you a lot about the mechanisms, but you lose a lot of the interaction among processes and among different processes and different sources, or whatever you say, different particles types. And we deal with this uncertainty by doing several things. First of all, we always do quality assurance, quality control of the data. We clean the data. We remove everything. We're very stringent about it. We remove everything that looks suspicious, even if it's true. We leave it out, because we are not working with the 99.9 percentile of something which you have very small amount of them, smally limited representation of these values. So we actually clean the data. This is the first thing which we do. Then we do different types of analysis. Actually, we do most of the time multiple types of analysis separately, and trying to see whether we converge to something which is reasonable across the different models. Then on each of the models, we do cross-validation or testing with data that was not shown, that was not seen by the model. So we put aside 20%, or we put aside 20% of the data, or 20% of the stations or the location, or something like this, maybe 10%, and do it multiple times. So we do it complete cross-validation. So we take 10%, we do something, we place them back, take another 10%. So we do it multiple times, randomly, oftentimes, or most of the times. And again, this gives us some assurance that what we get eventually, if we get something that we are happy to present to people, that we believe that there is something behind it, is okay, or seems to be reasonable at least. And we do sensitivity analysis. So sometimes we just plug in things and change things. For example, one of the sensitivity analysis that we use is bootstrapping. So you take the data, you blend it together, you know that real data possibly have some structure. I don't know the structure, but the physics know the structure, hopefully. That nature knows its structure. So what I'm measuring, or what I'm getting from other people that measure, and of course I trust people. So I trust the measurement, I mean, the people. So this is representing something. Now let's blend it randomly. Take it from here, plug it there, do the same thing, the same method that I use on the data. And this is bootstrapping, and you get something which is completely completely unidentified or not explainable, because when you blend the physics and you just get the same database without physics ordered in a reasonable way, oftentimes you don't get something that you can explain. So if you do the analysis on the true data, then do the same analysis on the bootstrap data multiple times, can be 100, 1,000 times of replicates. And you see that that the true data stands up, excel, compared to the bootstrap data, because the bootstrap data is, give you some variability, but nothing that you can understand. And the true data give you something that if you are lucky, if I'm lucky, I can understand. So again, this give us some evidence, not evidence, some support that possibly we were able to track something. We were able to identify through fingerprint of a process that you cannot measure. Because when you get the PM data, PM10, PM2.5, even AOD data, for sure there are processes that are hidden within the data, from day to day, from site to sites, and we don't know them because we are having only one parameter, AOD. Different AOD, different sites. What is the reason for different AOD? We don't know. But when you do the modeling and you check them and you get something that, in some location you have more absorbing and more coarse, and the other you have less absorbing and fine, and it fits what you understand about the study area, about what you know from daily life, about the situation. For me, it's somewhat assuring that I'm not providing full anecdotal data. It's something behind it. but it needs to be rechecked by other people.
Okay, thank you, Carlos, and for the answer. Is there alguna otra pregunta? Iván, gracias.
Thank you, Doctor, for such an interesting talk. It's been quite revealing, the method you have been applying to study the data and to analyze the information that you have presented. And something that is quite interesting is that with the development of the new low-cost sensors several years ago, we were all expecting that the deployment of this kind of sensors would help to enhance the capabilities of all the monitoring networks worldwide. But as you mentioned, with time, it has been noticed that it's not as cheap as it was expected. And that's because partially two things. The first one is that you have to replace constantly, I would say maybe year to year, the sensors. And of course, in time, that's going to add high cost to the initial investment. And the second one is the maintenance. So if you have to pay a lot of labor rather than for other consumables, it's going to represent a huge investment or a huge spend of money for the governments in particular for those cities where there are no AQMs, I mean, standard reference methods, right? So I would like to hear your opinion about what if you expect that in the future, this kind of networks would prevail worldwide, or if, well, it's in the end, it's going to be just spread as at the moment. I mean, just to help support and to give some information, but not become so available worldwide as at the moment.
So this is a hard question. I want to say the following. First of all, I believe in technology. So I'm sure that the technology will improve over the years and we will get better sensors at the same price. Let's say technology improve, price would not increase, probably, or hopefully. So we will have better technology in the future. Nonetheless, I do think that it is problematic to spread this technology across the whole globe or across the whole country. Big country like Mexico, it's very, very costly. And I believe that we need to be clever to decide when, where, and why we want to deploy the system, and maybe to deploy it for limited period and take the same sensor before they die completely, move into another place for another work, another research of different person or something like this. As I said, the information the information is provided by these sensors is complementary. Not necessarily chemically complementary, but complementary because we can deploy them at much higher spatial resolution, and they report at much higher temporal resolution because they report every minute or something like this. So if the application is something that we are interested in, either high temporal resolution, then standard AQM that report in Israel every half an hour, but in many other places in the world, every 1 hour, for example. So if we need higher temporal resolution, we can use them. If we need higher spatial resolution, certainly we can use them because, again, I know that in Israel we have about 150 AQM stations spread very heterogeneously. Some people, some communities, some cities, actually there are cities, that means they have large community, larger than 10,000 or 20,000. And in these cities, there is no AQM monitoring. Why? Because in Israel, AQM deployment is also political. I mean, you need to be strong mayor of a city. You need to be maybe related to the governmental party, and you will get the chance to put air quality monitor station in your city. But not all cities are so. So there are some times, some locations, some reasons why to use this system. I'm not sure that we can. I'm sure that we cannot deploy them across the whole area and forget about AQM system, AQM monitoring station, because it will be much more costly to operate this system. They are dying very fast. They are not calibrated. I mean, they are calibrated, but they are dying of calibration is decreasing or diminishing, or I mean deteriorating. This is the right word, very fast, and oftentimes they are not maintained by professional people like the one that maintain air quality monitoring station, because air quality monitoring station had to comply with standards of either EPA or EU or WHO, World Health Organization, which require that the data will be complying with certain standards and standard protocols. But if you give someone very nice person to deploy 10 units of these sensors in his place, you don't want to drive 300 kilometers to there. You send the sensor and he will deploy it and collect for you the data. He is very nice. He may be having third degree in physics, but it doesn't mean that he knows how to maintain this sensor. It's not the same. And if you get data that is maintained by not a professional person, that is maybe technician but passed a certain course how to maintain them, you may end up with poor data. So I think that the bottom line is, I think that this type of technology would fit specific question. You want specific question. You get a question whether this landfill site is affecting this neighborhood in Mexico City. Okay, if we have sensor that can measure something that is emitted there, methane or whatever, ammonia, that is measured in the landfill, in the neighborhood, and in the other side to look at the different wind direction and in different location, etc., etc., etc. Maybe we'll be able to say whether this landfill is affecting the community or not. And this is enough. After we do a nice job, we should take them out, and they don't need to be there for a thing for a very long time. The question was whether it is affecting or not whether it can monitor ammonia or methane for years as a greenhouse gas pollutants. If you want to measure greenhouse pollutants for years or for these are not the sensor. Probably you need much better sensor deployed in fewer locations, highly maintained, and luckily we know that CO2 is supposedly well mixed in the whole atmosphere. Actually, if you look at maps, you know, for example, that methane is not well mixed in the troposphere, but okay, let's say that it's well mixed, and with few locations we can measure them and get some idea about the levels, the increasing level of greenhouse gas, specific emission, specific concentration of specific pollutant.
Ok, gracias. Bueno, yo creo que paramos aquí porque tenemos otro compromiso a la 1:30, que ya es la 1:30. Muchas gracias, doctor David, y gracias a ustedes por su tiempo. Muchísimas gracias.
Thank you.
Tenemos un pequeño convivio para los que participaron, porque están aquí todos invitados.